Anyway, okay, so real quick, I just wanted to go over just a small review of where you see this stuff. Again, I've actually been really bad about doing simple quantum mechanical problems, which is where we're still at, but we're actually moving out of that today. Particle in the box, we've also talked about the finite barrier, which is where we get the concept of tunneling. Okay, particle in the box, again, there's, here it is, and so you're thinking maybe like, so what? Particle in the box actually brings up a whole bunch of concepts, and here I'm just drawing some of the wave functions. Here's the energy. Where you see particle in a box type properties are in things like molecules, and this is one of my favorite. This is called a cyanine. This is a cyanine dye. Dyes have families. There's a xanthine dye, cyanine dyes, Bo-Dippy dyes. I'm actually a chromophore chemist, so I know all the dye families. Cyanines are infrared dyes, red to infrared. And what happens is the way dyes work is they have to have big dipole moments. Hopefully you've heard that a optical transition is due to a dipole change. Hopefully you heard that in freshman before, or you heard it somewhere. And of course dipoles are electrons. So the way dyes work, the way dyes are engineered, is that you've got a negative and a positive end. Here's the positive end. This is simply, it's not negative, but it's less negative, so that works. Amines have some free electrons as well. So what happens is those free electrons pop over to here in the first excited state over this L, over this length, right? And that's a big dipole change, and that's what makes it a good dye. Now, because this length is so long, energy is proportional to 1 over L, that makes it kind of red, a very red dye. What about this one? You see, all you have to do is add some double bonds. I just drew in 2 extra double bonds. What would that do? So again, you know enough now as freshmen. I said these are 2 dyes. Tell me about what do you think the differences are, aside from one of them is longer than the other. You probably would have no idea. You could probably make some guesses, but they would just be wild guesses. What do you think would be different from this dye to this dye, given that this one is longer?
More infrared.
More uncertainty in position.
No, it's infrared. It's redder. It's lower energy. Right now, if you really want to get into the weeds, remember that it's what we're talking about is ground state to first excited state. So it's this energy splitting. It's that energy splitting that gives you absorption and emission. Those are really the same thing. And the longer it is, so that's kind of a detail, but it really doesn't matter. The difference, the energies and the differences in energies is proportional to 1 over L. So this just happens to be red. I actually thought about telling you it was blue, but that's also a lie. It's really red. But you link them down, they become infrared. So anyway, that's a particle in a box behavior. So you can look at molecules now and start to understand a little bit about their electronic structure from what is a really just stupid simple, just to get you used to quantum mechanical type of problem. Tunneling is important for protons tunneling. Tunneling is very important for protein structure because protein structure has a lot to do with whether things are protonated or not. That gives things charge. Charge is one of the things that gives protein like secondary structure, secondary, tertiary structure. Those are what cause proteins to have function. If a protein structure changes, it can turn from a protein to a prion. A prion gives you mad cow disease and Alzheimer's. So those are pretty bad. And protons are really good about tunneling. So that's one example. The one that you find on Wikipedia, which is where I got this, is radioactivity. So did they ever let you take home any of the nuclear stuff? No? Oh, come on, just a little bit, right? Yeah, you have. So it turns out that when a nucleus is heavier than lead, they're going to be radioactive. I mean, everything's radioactive, but what happens is that the strong nuclear force is what holds nuclei together. Now think about that. The nucleus is a bunch of positive particles, a bunch of protons. Those don't want to be together at all. Those have Coulombic repulsion. And, one charge, when they're right next to each other, remember Coulomb's law says that the energy is proportional 1 over the distance. They're basically touching each other. Those are pure charges that are basically touching each other. The repulsion is gigantic. Nucleuses should be exploding right and left, but they don't. That's the strong nuclear force. Now, when you get to heavy elements, they'll start emitting alpha particles, which, by the way, is just a helium-2 plus. And the reason it does that is the strong nuclear force just simply is no longer competitive with the repulsion anymore. All those protons repelling each other, the strong nuclear force is just not competing with it anymore. And some of the positive, right, a positive particle, right, starts shedding positive charge, some of them start coming off. It turns out to be a tunneling phenomenon, so the standard model for this, remember we're in a radial. I'm just drawing, this is one-dimensional, it's really three-dimensional, but anyway. So I'm looking at the nucleus, and so what you say is that the alpha particle is trapped in the nucleus. If it gets outside the nucleus, what it experiences is a very strong repulsion. Now that's because, remember, a nucleus is positively charged, and an alpha particle is also positively charged. So these are repulsive, right? And so that's what this dotted potential energy surface is, a Coulombic repulsion. So the reason that things decay, the reason that we have radioactive decay, is because the alpha particle tunnels outside of that Coulombic barrier. So just an example of tunneling. Anyway, so I just wanted to make this stuff relevant, just beyond, here's just a problem you can solve in quantum to learn it. Not that that's not fairly valuable. And now I want to move on to something really horrific, which is, at this point, I think especially on your homework, I had you do every other type of flat potential surface. Every question I can think of with any flat potential surface I can think of, I have you work on that. The answers to your homeworks are always make the wave function 0 at x equals 0, or make them smooth and continuous at x equals L. Anyway, not that that's specifically the answer, but that's the idea. So that should drum that into your head, which is unfortunately the end of the wave function is either sine or cosine or a e to the ikx plus b equals b e to the minus ikx. We don't really have anything else more to do with that, especially because, like I say, that homework is the last thing I really have for you that you could answer relatively easily. So now what we want to do is this. And I warned you that this was coming up. Potential energy, but not flat. So again, flat potential energies, steps, even an infinite barrier, sure, whatever. They end up still being really easy. It's smooth and continuous. We've done examples, you do them on your homework, not hard. What happens when there's some curvature to this? Oh man, all right. The real biz knocker is right here, right? So remember that freaking double derivative makes all of this a second order differential equation. Mathematically, I'm sure that there's insanely hard questions that big equations that go 10 miles long. I mean, technically, if you want to just start writing letters down and squaring and taking derivatives, I suppose that there's an infinitely large number of equations that could be solved. But the reality is this second order differentials are the worst. So we're just going to barrel past flat potentials and get into this. And I'm going to start with vibrations. And so the potential is going to be x squared. Right, that's kind of obvious. Anyway, I'll review Hooke's law and all that in a second. But I want to point out to you, how does a second order differential equation work? I did have the last Friday's extra lecture, I did show you a little bit more about how mathematicians approach second order differential equations. You really probably should watch that one. I really wouldn't call that one quite so optional because it's going to be kind of useful for what's coming up. But let me just point out how this really works, because this will help you wade through some of this. Okay. The thing about this guy, the reason that this is now a Bismarcker is that it now has the letter X in it. So like for a vibration where the potential energy scales with potential squared, right? So it's a parabolic. You know that bonds are like parabolic. They're like springs which have parabolic potential energies. The potential energy is basically X squared. Okay. Now, so what you've got is basically X squared times the wave function equal to the wave function times a number which happens to be its energy, whatever. The X squared has to disappear. This part has to be eliminated. Now, where does that occur? Given there's only one other place I can point to. Here. Right, so you see what's going to happen? When you do the double derivative, and this is just a simple subtraction, when you do the double derivative, what this SOB turns into is E psi. So this double derivative has to get broken into two during the double derivative. Part of the double derivative has to return this, but it's also going to have to return this. You see? And you see why? Because then when you add it to this, which is, of course, part of the Hamiltonian, you end up with... See, I mean, it's kind of, right, it's like I can explain this to an elementary school student, right? You know it's going to be a little bit more complicated when it comes to doing the double derivative. But again, just note at how this is engineered. You have to have a solution such that when you do the double derivative, the part you want comes out, but it's got to work to eliminate the potential energy at the same time, or it's not a real eigenvalue equation. If it's not a real eigenvalue equation, it's whacked. So anyway, so look for that. That's how these things are engineered. And reality is, once I come up with the potential energy and I write down the full Hamiltonian, what you do is you go look through a textbook prepared in 1790. Seriously, all the problems we're coming up with from now on, they were all solved around 1790 by just a handful of mathematicians. Of course, they didn't call it quantum mechanics. They were just, I don't know, I mean, you know, that was a long time ago. I have the feeling that they just simply wrote down equations and said, hey, let's write down an equation and see if we can solve it. I think that's literally what they did, which was what they did for fun back then. And then they died of cholera. All right, anyway, so, well, kind of. All right, so anyway, okay, let's get back to vibrations. And what we're doing are bonds, so let's make it a CH bond. And of course, bonds are from electrons. We're not describing the quantum mechanics of electrons, we're just going to describe a bond. From the analysis we're going to do today, you can describe infrared spectra. So not many of you are in PChem lab, but that's a big part of PChem lab is a big, one of the modules is infrared spectroscopy. Okay, just to remind you, don't write this down, I just want to remind you, you know this. So I'm not going to put this on any test or anything, but you remember Hooke's law? Hooke's law states that the force on a particle is a force constant times the displacement. It's a spring, right? There's a linear restoring force. So when you stretch a spring, depending on how far you stretch it, the force to return is linearly proportional. And of course, you have a constant of proportionality. If it's big, it's a stiff string. If it's weak, it's maybe literally, instead of a spring, it's a string. It also makes the units work. You know, you always have to have something that makes the units work. And hopefully, and actually I just wanted to bring this up in case you had forgotten some of your mechanics. I like to remind myself of this every now and then, like I'm doing something professionally or I'm at a conference, and it's like I keep forgetting that how this stuff works, and it's kind of embarrassing. I should remember this. Okay, and we're solving a very simple first order differential equation. Not that, I mean, this is almost not even applicable to what we're doing because it's so simple compared to a second order. First order differential equations are just a joke compared to second order differential equations, unfortunately. Okay, now from this, you see that the potential energy is 1/2 the spring constant times the displacement. So here's how we get a parabolic potential energy surface. And again, don't even write that down, that's not important. Okay, now here's the thing we're going to do to make our lives a lot easier, like a gazillion times easier. You've done enough flat potential surfaces to know that it really doesn't matter where we localize the surface. It's kind of arbitrary. We're always going to integrate from minus infinity to plus infinity anyway. So let's just reset the potential surface somewhere friendly. Let's just call it 0. And that's just going to make all the subsequent analyses like way easier. What you have to do is make sure that you understand that the wave function, or wave function squared, is the probability that you're displaced from equilibrium. So instead of the wave function describing where you're at, it describes how far you're displaced from where you should be at. It's such a minor reinterpretation, it just doesn't matter. And of course, it's going to make all of the rest of the stuff I'm about to write like a bazillion times easier. So of course, we're going to stick with that. Now, let me write down the full Hamiltonian, and let me show you what I'm going to do from now on. I was talking to some of you, especially so many of you are engineers. Really, you know, when I first started here, 342, 346 was half engineers, half chemists. You are 80% engineers, 20% chemists. And actually, last semester, you were 80% engineers, 19% chemists, and 1 geologist. He had about the highest grade in class, by the way. You should all feel ashamed. God, I should have brought that up. I've been meaning to bring that up like over and over. Yeah, I know, the guy's probably a genius, right? He did pretty well, but he didn't come back. But let me show you what I'm going to, well, here, let me write down the Schrodinger equation. So now when I say I'm writing down the Schrodinger equation, kind of like how, remember, I like to say wave function or Hamiltonian. Hamiltonian is a special operator. Its eigenfunctions are special, so I tend to call those wave functions. If I'm talking about an operator that's not the Hamiltonian, I tend to call them eigenfunctions or eigenvectors. I try to bias my language in that regard. And all of that's just stupid. It seems like scientists should be more careful with language and not have multiple words for the same thing, which is unbelievably annoying. Regardless, when I say I'm going to solve the Schrodinger equation, what I usually mean is that the operator I'm working on is the Hamiltonian operator. Remember, we think of those wave functions of the Hamiltonian operator as the real wave functions. And okay, minus a squared over 2m, which you're now sick of, which is good. And now remember, in the next lecture, I'm just going to introduce multidimensional quantum mechanics. I'm going to show you a 2D particle in a box. There's really nothing to it. Okay, here's potential energy. Oops, KF. I'll put that little subscript. I know it's not common to see the little subscript put there, but I'm just going to put it anywhere because I think that's how the book, how its notes are. Okay, there we go. Okay, now, I can't quite remember. It was almost 25 years ago, I guess, that I was in your shoes. And I can't remember if we saw the derivation from here. I actually, if anyone's really interested, I have this, it's the craziest thing. I have a textbook on semiconductors, which has 5 chapters on quantum mechanics. It's like the best, it's like graduate level, but it's the best textbook I've ever seen on quantum mechanics, although it's not about quantum mechanics. It's really weird. I have no idea why the guy did this, why he put this in there. Regardless, you know, between this textbook, if anyone's really interested, I can show you this. You can get a copy. Or look online. You can find how this is derived. It's about 5 or 6 pages of equation, next page, equation. And it's not that bad. It's relatively followable. It's just that, you know, it would take probably 2 lectures for me to go through it. You have enough math to follow along, but I really don't want to blow 2 lectures on just a bunch of stuff that you can kind of follow to get to the result, which here's what I'm going to do. I'm just going to write down the results. So this is one of the, you know, one thing that is kind of interesting about the Schrodinger equation for vibrations. This is one of the few times you use the Schrodinger equation to solve the wave functions. You can actually do that. And as you've seen many times before, remember I kept telling you this was the case. Often you don't use the Schrodinger equation to solve the wave functions. Like on your homework, if you haven't looked at your homework yet, it's a bunch of flat potentials. You never use the Schrodinger equation. You just use boundary conditions. One of the few times you actually use the Schrodinger equation to solve the Schrodinger equation. 5 pages of algebra. I don't really want to go through with it. In fact, I really don't want to on the remainder of the class. We've got like 4 more example things to go through. Vibrations today. Then we're going to cover rotations, and then we get to the hydrogen atom. What I want to do is just show you the Hamiltonian, and then show you the answer without doing days and days of calc, mostly algebra. It's like algebra, 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 calc, algebra, 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 calc. I swear to God, it goes just like that. So instead of doing that, let me just cut to the answers, and then we're going to like take them apart. Especially when we get to the hydrogen atom, there's multiple parts to it. We can see what each one does. We can also double check that they are solutions to the Schrodinger equation. So we'll just use the Schrodinger equation to check the answers. So, and I noticed that more and more. I check what other people do in other classes. Almost everyone's doing it this way. I'm a little perturbed at, I think there's some value to spending 2 or 3 days going through the bloody mathematics, but man, it still sucks. So anyway, my long-winded blah, blah, blah is I just want to show you the answer. And the next homework especially, you're going to be doing a lot of stuff with that. A lot with these these vibrational wave functions. And there's some neat things you can do with them, and I'll show you some of them today and tomorrow. Okay, so what happens is, when you solve this thing, remember x is actually the displacement from the bond equilibrium. When you solve this with that 5 pages of algebra with calc mixed in every now and then to solve the second order differential equation, what you end up with is an infinite number of answers. And while the mathematician may be like, well, yeah, I mean, I can write down answers all day long, we chemists know that one of them is special because it's the ground state, the others are excited states. So anyway, so I asked the mathematician to solve this. The mathematician can do it in 5 pages of algebra, but they come at you with like multiple answers. Now, they have a formula to transition between answers. Now, what does that mean? It means I can give you what I, as a chemist, know to be a ground state, and then I can give you a formula that we call, like, it has a special term, it's called a generating function. Or another term for it is a recursion. So I have a formula that turns the ground state into the first excited state, the first excited state to the second excited state, yada, yada, yada. And that's what the mathematician gave to me, and of course I fill in the details, like what is just a constant to the mathematician is actually a constant to me too, but it's h bar over 2m, and anyway, blah, 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 blah. Okay, so here's how that works. Now there's a normalization that depends on which function you're talking about. And that's what I mean by this little nu here. This little nu is a quantum, why am I using the letter G? It's a quantum number. It's the same thing as n in sine n pi x over L. N was a quantum number in the particle in a box. And of course, n equals 1 was the ground state, n equals 2 is the first excited state, n equals 3 is the third excited, anyway, blah, 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 blah. When it comes to the answer that the mathematician gave to me, they actually didn't start, this quantum number thing didn't start with 1, which makes sense. It started with 0, and then it goes 1, 2, 3, on and on and on. Of course, there's an infinite number of answers, with 0 corresponding to the ground state. Okay, so again, the mathematician gave me an infinite number of answers, but that one I know to be special, that's the ground state. So the wave function has a normalization that depends on whether I'm talking about the ground state or the first excited state. Okay, this is where it gets a little bit, this is the complicated part. That is called a Hermite polynomial. I'll show you those in a minute. What this guy, now normalization's normalized, so you really don't ever have to think about that again. This is the thing, that's the business end of the thing. That's the thing that turns you from ground state to first excited state to second excited state. Again, it's a Hermite polynomial. I'm going to spend quite a bit of time on this. Then that's about it. Then we have, guess what, e, everything is e to something, right? E to the x squared over 2 alpha, be really careful. I am trying to be as careful as possible. 2 alpha squared. That is not alpha alpha squared. It's not 2 squared. 2 alpha squared. It's the best I can do. I'm trying to be as careful with that. For alpha, right now, where's all my constants? Right? Where's my m? Where's my kf? It's all right here. H bar squared over m. Force constant to the 1/4 for some reason. That makes me uncomfortable. I don't know why, but anyway. Okay, so there you go. Those are the answers. And so what? Okay, so the ground state. What was the question? Let me just draw the ground state. And remember that we're starting at 0, which is really the equilibrium bond length. And as usual, remember that I like to put 2 graphs at once. So here's potential energy, and I'm going to just do this very lightly. Here's the potential energy, so right, it's just x squared. Right, it's just x squared. Okay, but now I'm going to draw the wave function on top of that for the ground state. And these little borders don't mean anything, right? I'm just trying to make a nice graph. It's not a particle in a box, right? So it can go, I don't know why I drew these little lines up and down. It's not a particle in a box. There's no infinite potential anyway. Okay, anyway, you know what this function is? You should be unbelievably familiar with this. It's e to the minus x squared. Bell curve. It's a bell curve, right? Right. Now this is very similar. It's very similar to many of your Maxwell-Boltzmann distributions, your probability distributions. Remember the square. Don't forget that the square of this is a probability distribution. Don't mess that up. Anyway, it's a bell-shaped curve, or a Gaussian. That's the actual term. It's a Gaussian curve. Yeah, you should. Gaussian curves are bell curves. Those are kind of important for a bunch of things other than. And it's lopsided, you know, it's because I'm right-handed and I'm looking at it. Nothing could be lopsided or the world will explode. The cats will die. Okay, so there we go. Oh, it's still not perfect. Anyway, that's the best I can do. Okay, so that's the ground state. And we're going to talk a lot about the shape of this. And there's all kinds of things we can unpack with this. Regardless, let me get to this Hermite polynomial thing, because this is where a lot of the action is at. So you can tell, by the way, it shouldn't be too hard to tell, that the ground state, remember that's, if I'm talking about the ground state, I have to tell you that the quantum number is 0. I have no other way to express that. That is the proper way to tell you what I'm talking about. Nu equals 0 is ground state. The Hermite polynomial is just the number 1. Normalization is whatever the hell it feels like it to be. And maybe I'll give you a really easy question on the test and have you solve the normalization constant. It would be unbelievably simple for you to do so. Anyway, so the first Hermite constant is just the number 1, and e to the minus x squared is just a bell-shaped curve, so that all makes sense. Okay, but now what about excited states? Okay. I might throw this on a test too. This really doesn't have much to do with P-Chem. It should be a giveaway, but I kind of like throwing this at you because it shows you, it tests your ability to do some mathematical things that should be simple, but sometimes it's like saying a difficult word, supercalifragilisticexpialidocious. Anyway, I can't even do that. So what happens is there is a recursion to get you to the higher states, and it works like this. What you do is, let's start, so this is a bit of an aside. You start with your present state. So let's start with the ground state. Okay, now be really careful be careful when you write down what I write down. Be careful. I'm doing this in a very controlled way, which is for me, but I'm going to have to look at my notes very carefully. Okay. I've left some space there, right? So I want to turn my present wave function into the next wave function. How do I do that? Okay, so I have my Hermite 0. I have my Hermite 0, and I want to get that, I want to turn that to the Hermite function for the first excited state. How do I do that? The recursion tells you, take what you have and multiply it by 2x over alpha. Make sure you don't get those 2's and alphas confused, right? My 2 and alpha are almost identical, just handwriting. Okay, so take the present Hermite polynomial. We obviously start with the ground state, multiply it by 2x over alpha. Subtract from that 2 times your present quantum number times the Hermite polynomial minus 1. Now you see why you should be able to do this, but I swear to God, you will be like angry trying to work these problems because it's going to confuse the hell out of you, even though it should. Well, look, how hard can this be? Okay, well, let's do one of them. Okay, with this being one, and the normalization is the normalization, that's never hard. I can draw the ground state, but now let's do the excited state. The excited state, the first excited state is nu equals 1, quantum number of 1. Okay, here's how to do that. The way to do this is to say, okay, well, I have the first state. I have the first state. Nu is equal to what? 0. That's what will get you. Exactly, I do that too. Nu is equal to 0, and I'm trying to get the nu equals to 1. Here's the thing. Recognize that the nu, the quantum number in this equation, is actually still 0 to give you the first one, right? You have to kind of reset your head. Okay, to get to the next one, you're actually working with the first one. Okay, so nu is equal to 0. This is 1. This is 2x over alpha. Okay, now let's do the next part. Minus 2 times 0. Yeah, 2 times 0, so that's it. Right. Now, especially because we have to add the Hermite polynomial of the minus 1 state, which doesn't exist, but that's okay because I multiply it by 0. Okay, so that's it. Now I've got an x. Let me draw what that looks like. And I'll use the next board. So what it does is, well, let me think you're perfectly capable of multiplying what I just drew with a line that goes through it, but just in case. Let me do the next excited state. There's not much to this. It kind of happens. I've done this so many times. I've got this memorized. I won't draw the potential energy surface. You should know that you're fine. It actually looks a lot like. A particle in a box. So there you go. I took this, you see I just multiplied the left half by a line that's negative and the right half. Actually, no wait, I inverted that, didn't I? I inverted that. It actually doesn't matter. See, that's the thing, I know too much about this. Mathematically, I know it doesn't matter, but you don't know that. So, anyway, so there's, and I'm not drawing these to scale very well, but anyway. Remember where I just drew this is arbitrary. I just feel like I need to show you some kind of y-axis. Okay, let's do the next one and then we'll just drop it. Okay, so let's do the next excited state. Okay, so this is now, to get to the second excited state, this is what? Nu is what? 1. That's right, this is 1. Okay, so H1 is x, 2x over alpha, 2x over alpha, so that's 4x squared over alpha squared. So I basically squared that first term. Minus 2 times 1. Right. 1. Minus 2. Minus 2. There you go. Yeah. So that means that the next state is, okay, the second excited state, I actually forgot what that looks like. How does that look? Hold on, if I multiply, Oh, hell, I forgot. I forgot what that looks like. What the hell is wrong with it? I think it looks like, this. I'm pretty sure. Yeah, it looks like that. Oh, anyway, I'll have to look that up. I'll use a computer to draw it. I'll get a handout or something. Anyway, so there you go. They actually do look a lot like a particle in a box, by the way. But they're slightly different. I'll show you how they're slightly different. I mean, yeah, they really do look like tremendously like a particle in a box. I should have worked that out before class. Okay, so let's see how we're doing. Oh, I fixed my watch. Okay, so what can I do with these? I'll tell you what, let me use a board. There's two things we can do with these. One is to get energies, and another to get average position. Let's do average position. And to do this one, and this will be a nice segue into the next lecture. If you don't have any questions, it'd be nice if you did. But,
is there a recursive harmonic? So around to iterate through like every, if you want to get to like the 50th, you have to go through the first and second.
yeah, I believe so. There's no formula to take you directly there. You have to go through step by step. You know, maybe there is, but I'm pretty sure there isn't. Maybe there is, I just don't know off the top of my head. Why would you see that movie?
Okay, that's right.
There may be. I'm not aware of one though. Okay, real quick. Let's do this one. Okay. So so again, the paradigm that I'm going to have from now on is set up a Hamiltonian and then do stuff with it. So relatively straightforward, right? Okay. What's the average position? And we'll do, let us do, what I want to do here. We'll tell you what. So for the first state, ground state, what do you think? What do you think? That's the wave function. What do you think it is? Oh, come on. 0, of course it's 0. Like, it's not even worth doing. Right? Of course it's 0. So the ground state of a CH bond is at its equilibrium bond length. That's what that means. Whoa. Not hard. Okay, let's do the first excited state. Okay. And I drew that wrong again. God, what's wrong with me? Not that it matters. I happen to know that mathematical, there's symmetry in math, and so it doesn't actually matter whether I got that backward or not. I seem to want to draw it backward. Okay, what do you think about this one? Okay, tell you what. I already heard someone mention the answer. Okay. Tell you what, let's just write it out. What we've got is, so we've got n for the equals 1 state. I won't even worry about that. You've got 2x over alpha. And again, I warned you, my alphas look like 2. You just saw that. E to the minus x squared over 2 alpha squared. Okay, then here's the operator. Remember, x operator is literally just an x. There's nothing to it. And 2x. Notice that the complex conjugate, remember this is the complex conjugate, but that doesn't mean anything for, this is nice because there's no i's in it. This will be the only thing that doesn't have an I in it, by the way, so all the other more complex things we're doing from here on out have an I in it, so look out for that. Okay, oh God, doesn't that look horrible?
Yeah.
Notice it's mostly just a bunch of constants, right? Yeah, I mean, I remember I told you that you might get freaked out by all of the, when I write things out and it's like, oh my God, how do I solve that? Well, it's just a bunch of constants, 90% constants. Okay, I've got 4n squared alpha squared. Hopefully that doesn't blow your mind. Remember, alpha is just mass times spring constant or whatever. Okay, I've got x cubed And then I've got two of these. I've got, what's e to the a times e to the a?
E to the 2a.
All right, e to the 2a. So this ends up actually being slightly easier. There you go. Right? So I had to write it out. It looks a little daunting. Reality is it's just a mess of constants. Then I've got x cubed times e to the minus x cubed, x squared. What do you think? Now, of course, on the homework, I would our homework or exam, I'll give you identities. But what do you think? Here's a hint. Is that, remember, that's our bell curve?
E to the minus ax.
Wait, that's a bell curve. Even or odd?
Odd. No, wait, even.
Even. It's a bell curve, it's even.
Odd.
What happens when you integrate an odd times an even function?
Odd.
It's an odd function.
The whole thing is odd. When you integrate an odd function,
It's 0. Across.
the integral 0. When you integrate a symmetric odd function, I mean, look at it. I'm integrating this. Basically, 0. Right, 0. So there you go. So it turns out that I believe in all the cases, this is the kind of thing you can learn from this. Bonds in the excited state still are on average at the same position they were in the ground state, on average. Although they do tend to spend a little bit more time out into the extreme a little bit. Okay, next time what we're going to do, this is one thing you can do with vibrational wave functions. Next time I'm going to show you some other little neat tricks. The next one I'm going to show you is this. We're going to do this one on Monday. We're just going to do the ground state. We're going to solve this not by an expectation way, not this way. Remember, I have to solve average x. I have to do that using expectation value. I have to do that. When it comes to energy, I'm actually going to use the eigenvalue equation. It's just a little bit easier. And then after that, I'm going to show you some weird predictions that come out of this. And then we get into rotation. Heads up, rotation